Recent XR research increasingly explores everyday surfaces as touchable surface, offering tactile feedback, reduced fatigue, and suitability for mobile use. However, touch behavior on curved surfaces, unlike flat ones, remains underexplored, limiting the extension of XR input space to diverse real-world surfaces. CurvedTouch addresses this gap by systematically analyzing how surface curvature and cursor mapping methods affect indirect touch interaction in XR. We evaluated 4 surface curvatures derived from body parts and 2 cursor mapping methods. Projection-based mapping moves the cursor based on changes in the projected fingertip position, while distance-based mapping moves it according to the cumulative 3D fingertip movement. We also compared near and far target distances to distinguish finger-only motion from whole hand motion. 16 participants performed tap, drag, and trace tasks in a VR environment using MetaQuest 3, OptiTrack motion capture, and conductive curved touch surfaces. We analyzed task performance, movement behavior, and usability. Results show that performance and usability degrade only on steeply curved surfaces. As curvature increases, users shift from finger joint-centric input to whole hand movement, stabilizing interaction by fixing finger posture. This explains why, in indirect touch, tap spread increased with curvature, contrary to prior direct touch findings. We also observed distinct clutching strategies. On low curvature surfaces, users strategically use clutching based on target distance. When the distance between targets is short, they attempt to complete the input in one go with minimal clutching. When the distance between targets is large, they actively utilize clutching to perform the input in multiple small movements. But on high curvature surfaces, clutching is avoided due to increased cognitive cost, and users move the maximum distance possible in a single motion, regardless of target distance. Cursor mapping methods showed no standalone performance and usability differences, but under high curvature, distance-based mapping provided better usability due to reduced mismatch between finger movement and cursor motion. Based on these findings, we propose design guidelines for interaction type, button size, interaction area, and cursor mapping, enabling XR touch interfaces to effectively extend beyond flat surfaces. We also propose an example interface applying these design guidelines. In the XR drawing environment, interfaces required for the drawing system are appropriately positioned, considering surface curvature. For example, the main drawing pad, which requires prolonged fine input, is placed on the desk with the lowest curvature, while the quick action panel, which has a small operational area and is used for short periods, is positioned on the lap area with the greatest curvature. The on-thigh QWERTY keyboard is an interface that places the QWERTY keyboard layout on the thigh, a surface with low curvature that offers performance and usability comparable to a flat surface. Reflecting the finding from this study that tap spread increases with greater curvature in indirect touch situations, the key size can increase towards higher curvature areas, such as the edge of the thigh. CurvedTouch systematically analyzes the effects of surface curvature and cursor mapping methods on XR users' touch behavior, providing design guidelines to extend XR touch input beyond flat surfaces to various curved surfaces in the real world. More detailed procedures and results can be found in the paper. Thank you.